To allow the replication of DNA, the double helix must be unraveled by an enzyme. Then, polymerase, another enzyme, moves along one of the strands called the leading strand in the direction 3 to 5 and assembles a complementary DNA strand as it goes along. On the other strand, called the lagging strand, the enzyme also has to read in the 3 to 5 direction. This causes a problem because the starting position 3 on this second strand is at the opposite end of the leading strand's position 3 and is not accessible. To counter this problem, polymerase begins reading the lagging strand further down its length. Before replicating the DNA, the enzyme places a primer to mark the spot where replication begins, and then reads the strand in the 3 to 5 direction towards the starting point of the replication on the leading strand, which corresponds to the left on this diagram. Once the enzyme reaches the starting point, it jumps forward even further down the length of the strand and copies another fragment of DNA. When the entire strand has been copied, the primers are replaced with DNA again in the 3 to 5 direction. As can be seen on the pale blue fragment, the final primer cannot be replaced because there is no 3 end available. Consequently, a fragment of the initial DNA is lost during every replication, resulting in much shorter DNA molecules after several replications. This is where telomeres come into play. They are repeated fragments of DNA present at the ends of our genetic material which protect our genes from the erosion of replication. However, after a certain number of divisions, the telomeres are worn out and no longer protect our genes. This leads to cellular senescence, or, in other words, the aging and death of the cell.